Hello and welcome back. Now today we are going to see the experiment to study the thermocouple. So in this experiment we are going to we have this experimental setup. Here we have one junction is a cold junction which is kept in a water, and other junction is a hot junction which is heated by using this burner. So we have to heat it up to 90 degree centigrade. Now, so I had kept this for heating, and then we have to measure the thermo EMF with the help of this digital multimeter. So first of all we will see what is the experimental setup. So the experimental setup is, you can show it here. So we have this one beaker is filled with water, and the other beaker, second one, so this is for cold junction, and other beaker is having sand. So this one is a water, so this is a cold junction, and the other one is obviously hot junction. So this is heated with the help of a burner, so I will draw a burner over here. Okay, so this is the actual experimental setup. We have one junction is at cold temperature, which is at room temperature, and the other junction is at say higher temperature. So cold, this temperature we have already measured, this is 30 degree centigrade, and this is at hot junction. So we are going to heat it up to 90 degree, and then we are going to take a cooling graph for that. Okay. Now according to Seebeck effect, whenever there is two junctions, they are made up of bimetals. That means what? They are made up of two different kind of metals. Then whenever we have such two junctions, and one junction is kept at a lower temperature and other junction is kept at a higher temperature, then in that situation there is a thermo EMF is generated. So this effect is called as Seebeck effect. It has got so many applications. Say one of the application is nothing but in the field of sensor. Say for example, if you want to measure say higher temperature, then this mercury based thermometer or alcohol based thermometer, they cannot be used for measuring higher temperatures. Say, so for that purpose we can use a thermocouple sensor, and that can use the that can sense the temperature, that will give a voltage, of course thermo EMF, and from that we can sense what is the temperature. So this is one of the application. Also it is not very successful, but in some sort of thing we can generate the electricity also with the help of thermocouple. Say if we have one junction at a cold temperature and other junction is at hot temperature, then there will be thermo EMF. So using this simple principle we can generate the electricity also, but that is not very much successful till date. And so the main application of this type of junctions is in case of sensors for measuring the temperatures, higher temperatures, which cannot be measured with the help of mercury or alcohol based thermometers. So here when we go on increasing the temperature, then we get the graph of this in this type. So I will plot the graph here. So this graph is thermo EMF versus the temperature difference. I will call it as a delta T in degree centigrade. Then this graph will go like this, up to certain point it will go to a maximum, then this point we call it as Tn. So that is neutral temperature. Now till this Tn, as the delta T increases, thermo EMF also increases. But after reaching to the certain point Tn, which is the property of a different combination of bimetals, in that case what will happen, this temperature goes on decreasing then further, okay, and it will go on decreasing in this way, in the reverse way, if we go on increasing the temperature further, and there will be a certain temperature where this thermo EMF will go into the negative direction. So that is called as inversion temperature, we call it as Ti. Okay. Now in our case we will be operating this thermocouple much below the Tn, that is neutral temperature. This is neutral temperature, this is inversion temperature. We will be operating it much below the neutral temperature. So here once it reaches to above 90 degree centigrade, now already it reached to 120 degree centigrade. You can show it here with the help of camera. I will make this gas off, and we shall take the cooling readings now. Okay. So at different temperatures we have to note down these cooling readings. So now you can see that this is higher temperature, slightly higher temperature is there, 120 degree centigrade. So for that we are getting it as 4.2. Okay. Now here we have to measure this at slightly lower temperatures, say from 90 degree we have to go up to 35 degree centigrades. Okay. Now what I had done is, this experimental readings I had already measured, you can show it here, and so I will just write down them very fast, so that we can save some time. So it is for 90 degree centigrade, it is 2.5, then there is 2.1, then we have 2, then 1.8, then 1.6, 1.4, 1.2, 1.1, 0.9, then we have 0.7, 0.6 and 0.5. These are all readings are in millivolt. So when we reach to the room temperature, we get it as around 0.5, which is actually just above the room temperature, that is 35 degree centigrade. Now the next thing is, what we have to do is, we have to plot a graph here. So this graph will be this column against this column against this column. That means we have to plot a graph of thermo EMF, that is E in millivolt, against the delta T, that is the temperature difference in degree centigrade. So we have to take this scale accordingly. Actually this temperature difference will be nothing but what? It will be 5, then 10, like that. At the maximum we got it as 60 here, 60 degree centigrade, and these readings will be, say, starting from 0, then we can have 0.5 like that, and we will go to a maximum value of what? 2.5. I am drawing this for the purpose of explanation. You can take the proper scale on the graph paper to draw this. Now after this, you just plot this graph. So this graph will look like certain like this, and then find out the slope of this graph. Okay, now the slope of this graph will be nothing but what? Delta E divided by delta capital T. So you have to choose this point and this point. Say this is our x1, y1, and this is our x2, y2. So this slope will be nothing but what? y2 minus y1 divided by x2 minus x1. So this whatever value you get, that will be nothing but what? In millivolt per degree centigrade will be the unit of that. Okay. So this is what the experimental setup we have, and these are the calculations, and you can find out with the help of these readings what will be the final the temperature coefficient in millivolt per degree centigrade. I hope that you understand this experiment. If you have any kind of difficulties, you can ask me in the comment section, and I am very much thankful to the patience listening from all of you, and I am thankful to Mr. Abhi for helping me in recording this video. Thank you very much. Like, comment, subscribe, share. Thank you very much.